the driven victim. Usually the victim is driven by a gate that fights noise. The noise depends on relative resistances. The victim driver is in the linear region, then the aggressor is in saturation. And if the sizes are the same, the aggressor's resistance is 2 to 4 times more than the resistance of the victim. So you have two wires here, one is the aggressor and one is the victim. So the size of the coupling waveforms are dependent on the size of the victim. So as you can see here, an undriven victim will have 50% of the signal, and if the victim has a half size driver, then the signal that is coupled onto it is 16%. And if you have an equal size driver, the coupled signal is even lower, 8%. And if you have a double size driver, the coupled signal is 4%. So as you can see here, it is inversely proportional to the size. So what are the noise implications? So what if we have noise? If the noise is less than the noise margin, then nothing happens. So you remember we have what is the noise margin. You have, this is VDD, and you have the voltage, and which is the middle part is the noise margin, and this is considered as logic level 1 and this is considered as logic level low. So if noise is less than the noise margin, then it is okay. So the noise is within here. And if you have static CMOS logic, it is okay. It can remove the noise by connecting it to VDD and ground. So, and it has complementary logic gates, so it will eventually settle to the correct output even if it has large spikes, right? So for example, if you connect an inverter, this is an example of static CMOS logic. If this is has a noise, it will still produce a good graph because this transistor is pulled up or pulled down, right? But if you have only one transistor here, so if you have a noise here, it will be transmitted into the output. So the dynamic logic usually only has pass transistors. This is known as a pass transistor, and it doesn't have complementary logic. Never recovers from glitch. So if there is a glitch here, it will be automatically come out, whereas the glitch here does not come out at the inverter output. So these glitches can cause memory and other sensitive circuits to produce the wrong answer. What is wire engineering? Wire engineering is to design the size of the wire to achieve the desired delay and the desired area and power goals, as well as having acceptable noise. So you can design the placement of your wires based on its width, spacing, layer, and shielding. So what is shielding? Shielding is actually having the wire here. Shielding is having it connected, another wire beside here connected to ground to shield it. If it's connected to ground, then it will not create so much capacitance. So it can shield or protect the wire in the middle. This is the signal wire. Repeaters. Another way to remove the noise is to have repeaters. So let's look at this circuit. You have the driver at the input, and the receiver has another inverter. So let's see what happens if you have two inverters. So let's say your input is like this, the output of the inverter will be inverted, and you can get back your original signal by putting another inverter, and you get back your original signal. So this is for a long wire. So you add a driver, this is the driver, and this is the receiver. But if the wire is too long, this length of this wire is too long and it's too high, then at your signal here it might be distorted because your output here is too small. So in order to maintain the integrity of the signal, you can put in many repeaters inside the long wire so that the signal is always protected. Here, so it goes like this, and then like this, and like this. And finally, at the final receiver, it returns back to the original. So a good strategy is to break long wires into n shorter segments, and you drive each one with an inverter or a buffer. What is a buffer? A buffer is two inverters back to back. What should we use? So we should have enough number of repeaters to multiply the signal so that it doesn't degrade. So, and how large should each repeater be? It depends on the resistance and the amount of capacitance there. So here you can model the equivalent circuit of the wire, which is comprised of capacitance and resistance. So here the wire length, you can have you can calculate the wire capacitance and the resistance based on the length, and you can also calculate the size of the inverter, which will be inside the repeater, and you can calculate the capacitance of the inverter there, which is important here is the gate capacitance and the resistance in the inverter. So let's look at what is the actual size of the repeater. So here is the derivation for the size of the repeater. So what is important here is you do not need to know how to derive, but what is important here is to know the size of the repeater. So the size of the repeater or the inverter is known as W, and W is related to R of the wire, and CW, which is the capacitance of the wire, and RW, or the resistance of the transistor in the inverter, and the CW, which is the capacitance of the inverter or the repeater. So you can put this together and square root them. The wires which are important to design is the wires which are connected to the clock. So if you were to design a chip, your chip has many different blocks. So let's see the ALU, the multiplier, the flip-flop. Here, all these blocks have to be connected to the clock. And because each block has to be connected to the clock, so the clock will run very long wires inside the chip. So there is many strategies to do the clock distribution in the chip here. So if you can see here, the clock distribution is connected like a tree. So it will branch in the beginning here, the first clock, it will branch into several different layers and different branches. So you need a very high peak current to drive all this load. So the peak current here is related to the capacitance and the difference in voltage over time. So this dependent on the clock speed or the switching speed of the chip. So the power is also related to the capacitance, and the power is also related to the capacitance and the square of the VDD and the frequency of the switching. So if the chip runs at high voltage, high VDD, so the power will be squared, and it is quadratic. And if the chip is switching at a very high speed, so then the power is also increased. There are many strategies to reduce the delay. The capacitance here is dependent on the length of the wire. So we want to reduce the capacitance. So instead of connecting it this way, which will cause the wires to run very long in the beginning, and further here the length is very long. So you can reduce the length of the wires by connecting the clock into trees. Here it's known as the H tree because you divide, this is the input of the clock, right? It is divided into the right and the left, so there is equal length here. This looks like a H, so that is why it's known as the H tree. An advantage of this H tree is that it has equal length to the right and also equal length to the left. So this means that if you connect a block here, let's say a flip-flop here, and this another flip-flop here, so the timing delay for the clock signal to go this way, so let's say path A, and also path B to reach the other flip-flop, so the path length of A equals to the path length of B. Therefore, the delay of A equals to delay of B. So if you have equal delay, then you can avoid something known as the clock skew. So this is known as the matching delay in clock distribution. You can balance the delay of the path, and therefore you can match the buffer and wire delays to minimize clock skew. Clock skew means when the clock doesn't arrive at the same time. So if you have different length, the clock will not reach at the same time. So the point of having a clock is for timing, right? So when you have flip-flop here, this flip-flop, and you have another flip-flop here, and you have the combinational logic in between. The idea of having the flip-flop was so that you can have the same path here. The same time period T here is the same. But if your clock doesn't arrive at the same time, so let's say this clock for flip-flop A and the clock for flip-flop B is not the same. So this is the clock for A. If it is not the same as when the clock arrives for B, there is a slight delay. This is known as the clock skew. So the latch or the flip-flop which is driven by clock is data dependent. And if you have a clock skew, your data will be distorted because it is timed at a different clock, right? Sometimes there are also fabrication issues, and this is known as process variations, and this will also affect the timing of the clock. And IR drops or voltage drops. If for longer wire, it has higher resistance, so the voltage drop is higher, right, compared to a shorter wire, and the resistance is smaller, so the voltage is lower. So there are many different kinds of tools which can support the clock tree design when you design your chip. So let's look at the picture of a chip here. This is the Intel Itanium processor. It was fabricated in 0.18 micrometer technology. It has 1 GHz core clock and 200 MHz system clock. Okay, the size of the chip here, as you can see, is this is 21.6 millimeter by 19.5 millimeter. So here is the cache. Here is the array control, and there are 5 repeaters needed and 157K clock latches. So all these latches have to be controlled by the same clock. So how do you create a clock? You can have a system clock which is connected to a PLL. PLL is a phase lock loop, and then you can connect it to a synchronous circuit, and which is connected to a latch, and then connected to a ring oscillator. So all these are the blocks needed to generate the clock. This is the example of the core clock distribution. So for this distribution, you can divide it into the H tree, and this is the routing. So you can have the clock in this metal layer. So if this is metal 1, this is metal 2, right? You can, to protect the clock from noise, so we put something which is known as a shield. The shield is connected to either VDD or ground. So you put the clock in the middle, and on the side adjacent, you put a wire which is connected to VDD, so that the signal is shielded. If you know the wire in your lab, right, the signal runs in the middle, and the outside here, the outside ring is the shielding. We do the same thing in the chip. So you have the clock running in the middle, and it's shielded by metal 2 layers. So this is an example of the measurement of the clock skew. So as you can see here, in actual fact, the signal is not so clean if you zoom in at picosecond resolution. So you can see here there are possibilities of skew here, because the clocks don't arrive at the same time.